Today we're going to be talking about Pascal's triangle. And what Pascal's triangle is a triangle of numbers and concepts invented by Blaise Pascal in the 1600s. Now, all these concepts that are involved, and there's probably very, very many, they were all known to mathematicians centuries before Pascal came along. But he was the first one to make them all into one kind of solid math concept or math principle that people could use, and it was just really easy to use. Alright, so how Pascal's triangle is set up is the outer two most diagonal lines are going to be ones. No ifs, ands, or buts. No changing that. The second outermost lines on either side are going to be your counting numbers. 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, and so on until infinity. What people need to remember, and what you guys know, is that to get a number, for example, this 2, you have to add these two ones above it to get this 2. So same down here, you're going to want to add those numbers to be able to get the respective number that's supposed to be in between them. So for example, 3 plus 3 is 6. You can't get that 6 really any other way but adding the 3 and the 3. 1 plus 3 is 4. 3 plus 1 is 4. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And this continues all the way down the triangle to infinity. No way around it. That's how the triangle works. Alright, so big concept number one we're going to focus on is binomial expansion. Now, binomial expansion, you know that a binomial is basically two terms. And it's set up in the format a plus b raised to the x. So in correspondence with rows on Pascal's triangle, and you know that the top row starts with 0 and it keeps continuing on downward forever to infinity. X to the z, if you replace x with a 0, anything raised to the 0 is 1. Basic exponent principle. Anything raised to the 1 is itself. Now, 2 and beyond is where it gets a little tricky. What these numbers are the leading coefficients for each term. So you know that, for example, and I'll just go ahead and do this, if x were to be 4, you would look to the fourth row, which is right here. So you would be looking at 1, 4, 6, 4, 1. And if we come back over here a little bit for a little bit of space, you're going to look. That 1 is the first coefficient. You're going to use that a and this exponent. So 1 times a to the 4th. Look, second coefficient, 4. Now here's where things get a little tricky. You're going to decrease in exponents by subtracting 1 off each time you jump a number. So we'll be subtracting 1 off, and so forth like that. So then we get here to 6a squared plus 4a plus, alright, so we've covered all those and our a's. Now we need to cover the b's. B's are the same thing but backwards. So b to the 4, b to the 3rd, b to the 2nd, and b. So same thing. Subtracting 1 off, but we're going the opposite way. Instead of left to right, we're going right to left. So you've got a to the 4th plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the 4th. So that can work with any number that x is. So if x were 5, we just look down to the 5 and do our same thing. A to the 5, a to the 5th, a to the 4th, 3rd, 2nd, 1st. b to the 5th, 4th, 3rd, 2nd, 1st, and use our leading coefficients. And you've got to remember that you've got whatever b is, you have to replace every b with what b is. You can't skip out and say, I'm going to leave this b here. Same with a. Whatever a is, you have to replace all a's with it. And you always need to simplify. So if b was plus 5, you'd have to take 4a cubed times 5 and replace it with 20a cubed, because the 4 and the 5 are like terms. And anyways, we're going to move on to the second concept, explorations of squares. Now, of course, exploration of squares means we're going to be looking at some squares. So, big rule, always keep it. The number squared has to equal a counting number. So that means we are only looking at this group right here. And it's a lot easier if we look at it from the left. So for example, 2, 1, and 3. 2 squared equals 1 plus 3 equals 4. Boom, boom. Oh, you think it don't work? 6 squared equals 15 plus 21 equals, 36. What do you know? And in case you didn't know where I got 6 squared from, I got it from down here. 6, 15, and 21. So there you go. That's the exploration of squares. Big rule is that the number that you square has to be a counting number. It will not work in any other scenario, because if you try 10 squared, not when it's a counting number, 10 squared, it does not equal 30. Well, if you were to go all the way down here to counting number, it probably would work. And you can try that on your own, maybe as a little bonus assignment if you want to, just see how that works out. And so and also it can work this way. You just have to remember that in this case, instead of the counting numbers working like this, counting numbers work like that. So the 6 would still be squared. You just got to make sure you're not trying to square the 15 and figure out why 15 squared does not equal 6 plus 21, because that would be a nightmare. All right, so anyways, we're going to move on to the final concept, which is probability, or I'm calling it flipping a coin, because coin is the easiest way to demonstrate. So if you were to flip the coin 0 times, we just toss it. Toss the 0. It's out of here. Boom, boom. If you were to flip the coin 1 time, you either get heads or tails. 1, 1. What? Oh, you seen a pattern? How about 2 times? You can get heads, heads, heads or tails or heads, or all tails. 1, 2, 1. 1, 2, 1. Same with 3 times. You would get 3 heads once. You could get 2 heads and a tail in 3 different combinations. 2 tails and 1 head in 3 different combinations, or 3 tails in 1 combination. So 1, 3, 3, 1. 1, 3, 3, 1. Alright, so that's some of the big principles behind Pascal's triangle that can help you in school or wherever you think you might need them. And there's plenty more you can go out and find on the internet. It also helps you with, I know, the Fibonacci sequence, and I can always make another video detailing that if you want. It also detail like square roots of 11, how those work, or exponents of 11 working across the board, and so forth like that. But Pascal's triangle is really interesting, and I think you should definitely go research it